for example, find absolute max and absolute min for f of x equals x squared on the interval -1 to 2. Okay. All right, so according to what I said a moment ago, I should search for critical values and I should check endpoints. Okay. So find critical values. So I'll take the derivative and set it equal to 0. Looks like there's just x equals 0 is the only critical value, right? If 2x equals 0, then x equals 0. Only critical value. Now, is this critical value on my interval? Yes, it is. So therefore, it's important to me. If I had found a critical value which was not on the interval they gave me, I do not care about it whatsoever, even though it's a legitimate critical value for the function as a whole. It has no bearing on the problem at hand if it's not found in that interval. But this one is, so we're keeping it. All right. So the only other thing besides the critical value to be worried about is the endpoints, but they're given to me already in the problem, -1 and 2. So what I should do now is just find, right, compare values. Right? I need to find f of -1, the left endpoint, f of my critical values, and f of the right endpoint. Okay, so let's just see what we get. -1 squared is 1, 0 squared is 0, and 2 squared is 4. All right, so it's pretty easy to search through this. Looks like this is my absolute minimum. 0 is the smallest value I've found here. So there's the absolute minimum on this interval. Again, on the interval, not for the function as a whole, of course, on the interval. And absolute maximum is the largest value I found here of 4. So let's see in a picture what exactly did we do and what did we find here. If I draw x squared, I put in 0, I get 0. I put in 1, I get 1. Put in 2, we get 4. 2, 3, 4. So something like this. -1, 1, -2, 4. Okay, so there's a skeleton of our parabola here, something like this. Okay, that's reasonable enough. All right, so what did we do in this problem? We first narrowed our view from the totality of the function to the interval -1 to 2, closed interval, -1 to 2 on the x-axis. So along this x-axis subset here, we map up to the function values here and here. And we're looking, I'm just going to use dots instead of the closed bracket notation. We're looking at this set of values. Right? In this set of values, we concerned ourselves with the endpoints, right? The endpoints themselves, and the critical value happening here, where the derivative went to 0. Okay? And we found exactly what the picture betrays, that on this closed interval of function values, corresponding to this closed interval of independent variable values, we have that the largest value, the absolute max, occurred here, right? It occurred at 2 with a value of 4. Right? So the absolute max is 4 for this function on this closed interval. And we see the absolute minimum was happening here. It's not over at this left endpoint, right? That's too high. The lowest value is happening here. So absolute min value of 0. Okay. Happening at x equals 0. This one happening at x equals 2. Right? We've got an absolute min of 0, but again, on this closed interval, not for the whole. It happens to be that for the whole thing, this is also an absolute minimum. But that's not our concern in the problem. It doesn't have to be that way in general for these types of problems. The important thing is you can always find an absolute max and absolute min on a closed interval for a continuous function. And the way to do it is what we did, and that is find the critical values. It could be more than one. Find as many as there are in that interval. And all you do is compare the endpoints of the interval and the critical values inside the function. Whichever one yields the biggest value is the absolute max. Whichever one yields the smallest value is the absolute min on that interval.